Hello everyone, today we have to learn about complex variables. In this topic, we have to learn about analytic functions. First of all, definition of analytic functions. If single valued function w is equal to f of z is differentiable at each point of a domain capital D, then it is called analytic or regular or holomorphic function. This is the definition of analytic functions. Now, Cauchy-Riemann equations. First form, that is Cartesian form of Cauchy-Riemann equations. First equation is given by ux is equal to vy. Meaning of this, partial derivative of u with respect to x is equal to partial derivative of v with respect to y. Second equation is uy is equal to minus vx. Means partial derivative of u with respect to y is equal to minus of partial derivative of v with respect to x. Now, to remember these two equations, we can use this idea. Here, we can write dou u, dou v, dou x, dou y. Arrows in downward direction here also. Then, its ratio, dou u upon dou x, that is nothing but ux. Dou v upon dou y, that is nothing but vy. Second equation, you can consider like this: dou u, dou v, dou x, dou y. Okay, and now arrows are like this. This arrow indicates anti-clockwise direction and this arrow indicates clockwise direction. And we know clockwise direction, we have to denote it by negative sign. So partial derivative of u with respect to y, which is given by uy, is equal to clockwise direction minus partial derivative of v with respect to x. So these two are Cauchy-Riemann equations in Cartesian form. Now, Cauchy-Riemann equations polar form means Cauchy-Riemann equations in polar coordinates. First equation is given by ur is equal to 1 upon r v theta. R and theta are in suffixes of u and v respectively. And second equation is 1 upon r u theta is equal to vr. Theta and r are in suffixes of u and v respectively. Now, to remember these two equations, same idea, dou u, dou v, dou r dou theta. Then arrows in downward directions. So, partial derivative of u with respect to r, that is ur, 1 upon r, partial derivative of v with respect to theta. First equation. And then using this, partial derivative of u with respect to theta into 1 upon r. This one is equal to partial derivative of v with respect to r, that is vr. And here this is clockwise direction, so we have to put here minus sign. Okay. Now some remarks. Note number 1. Function f of z is equal to u plus iv is said to be analytic if it satisfies Cauchy-Riemann equations, above equations. And note number 2 is if f of z contains z bar conjugate of z, then f of z is not analytic function. Note number 3 regarding harmonic function. Function phi is equal to phi of x comma y is said to be harmonic function if it satisfies Laplace's equation. This is Laplace equation. Then function phi is said to be harmonic function. Second order partial derivative of phi with respect to x plus second order partial derivative of phi with respect to y is equal to 0. And then note number 4 is for conjugate harmonics or conjugate harmonic functions. If f of z is equal to u plus iv is analytic function, u and v are said to be conjugate harmonics of each other. Now note number 5 regarding orthogonal trajectories. If f of z is equal to u plus iv is an analytic function, then the curves u is equal to c1 and v is equal to c2, where u is real part of function f of z and v is imaginary part of function f of z. U and v intersect orthogonally, that is v is equal to c2. This curve is the family of orthogonal trajectories of the family of curves given by u is equal to c1. This is note number 5. Now we have to solve problems on analytic functions. Type number 1. In this type, we have to show given function is analytic. So this is example number 1. Show that function f of z is equal to z into e to the power z is analytic function. We have to solve this sum. Given function is f of z is equal to z into e to the power z. We know z is equal to x plus iy and e to the power z can be written as e to the power x plus iy. Now using laws of indices we can separate this. E to the power z can be written as e to the power x into e to the power iy. But you know e to the power I theta is cos theta plus I sin theta. So this is equal to e to the power x into cos y plus I sin y. Okay. Now if you want you can separate this. So e to the power z can be written as e to the power x into cos y plus I into e to the power x into sin y. Hence f of z is equal to x plus iy into e to the power x cos y plus I into e to the power x sin y. Now take multiplication of this bracket with this bracket. Then this is equal to, first multiply this bracket by x. X into e to the power x into cos y plus I into x into e to the power x into sin y. Now multiply this bracket by plus iy. So plus I into y into this plus I y into e to the power x into cos y plus I into plus I, that is minus 1 y into e to the power x sin y. Now collect real part separately and imaginary part separately on right hand side. So this can be written as real part is first term and last term. Collecting these two terms, x into e to the power x into cos y minus y into e to the power x into sin y plus I is taken common, and then we have to collect imaginary terms, second and third term. So from here x into e to the power x sin y, from here plus y into e to the power x into cos y. This is f of z, and here f of z is separated its real part and imaginary parts like this. So you can express f of z is equal to, we can write u plus I into v. Okay. Now comparing, u is equal to, we can write x into e to the power x cos y minus y into e to the power x sin y, and v is equal to, we can write this bracket x into e to the power x sin y plus y into e to the power x cos y. Okay. Now we have to find out partial derivatives of u and v with respect to x and with respect to y. So partial derivative of u with respect to x is equal to partial derivative with respect to x considering y as constant. So this becomes constant, and we have to take derivative of this applying multiplication formula. So this becomes cos y first function as it is, derivative of second plus derivative of first function into second function as it is, minus here we have to take its derivative with respect to x. So y into sin y becomes constant, and derivative of e to the power x is e to the power x itself. So this can be written as minus y into e to the power x sin y. This is partial derivative of this term with respect to x. Then ux is equal to x e to the power x cos y, taking multiplication of cos y with this bracket, plus e to the power x cos y minus y into e to the power x sin y. Now take partial derivative of u with respect to y. Uy is equal to. So derivative of u with respect to y, considering x as constant, means x into e to the power x becomes constant. So x into e to the power x, and derivative of cos y with respect to y is minus sin y, minus x into e to the power x sin y. This is partial derivative of first term. Now partial derivative of second term with respect to y, considering x as constant, e to the power x becomes constant, minus e to the power x, u into v formula, y as it is, derivative of sin y, that is cos y, plus derivative of y with respect to y is 1 second function sin y as it is. Okay, now simplify this. This is equal to minus x e to the power x sin y minus y e to the power x cos y minus e to the power x sin y. This is partial derivative of u with respect to y. Similar to this, we have to find out partial derivatives of v with respect to x and with respect to y. Vx is equal to derivative with respect to x, considering y as constant, sin y, applying u into v formula here, x as it is, derivative of e to the power x is e to the power x, plus derivative of x is 1 into second e to the power x as it is, plus derivative of this with respect to x can be written as y into e to the power x into cos y. Okay, simplify this. So Vx is equal to x into e to the power x into sin y plus e to the power x into sin y plus y into e to the power x into cos y. Similar to this, we have to find out partial derivative of v with respect to y. Vy is equal to partial derivative with respect to y, considering x as constant. Derivative of first term of v with respect to y is given by Vy, which is equal to x into e to the power x, derivative of sin y is cos y, plus now derivative of second term with respect to y, e to the power x is constant, into bracket derivative of y into cos y with respect to y, minus y sin y plus cos y. So this is partial derivative of v with respect to y. Let us compare ux and vy. Ux is this one, x into e to the power x cos y, and here also x into e to the power x cos y. This is same term. Then second term, e to the power x cos y. If we take multiplication of e to the power x with this bracket, then we should get e to the power x into cos y. And third term is minus y into e to the power x sin y. Taking multiplication of e to the power x with this term, minus y e to the power x sin y. Same term. Means from this and this, we can say ux is equal to vy. So we can write ux is equal to vy, which is equal to x into e to the power x cos y plus e to the power x cos y minus y into e to the power x sin y. Let us compare uy and vx. Here uy is minus x e to the power x sin y, first term, and from here x e to the power x sin y with plus sign. This is positive and this is negative, same term. Now here negative term, y into e to the power x cos y, y into e to the power x cos y. This is negative and this is positive term. And third term, minus e to the power x sin y, and here third term is plus e to the power x sin y. Means uy and vx are having same values with opposite sign. So we can write uy is equal to minus vx, minus of vx, and this is equal to minus of x into e to the power x sin y plus e to the power x sin y plus y into e to the power x cos y. So from this equation and this equation, it is clear that Cauchy-Riemann equations are satisfied. Hence we can say given function is analytic, and result we can write like this: Cauchy-Riemann equations are satisfied. Hence f of z is equal to z into e to the power z is analytic function. To show given function is analytic, first of all we have to put z is equal to x plus iy in given function and separate its real part and imaginary parts like this, and compare this with u plus iv. Find u separately, find v separately, and then partially differentiate u with respect to x, partially differentiate v with respect to x, as well as partially differentiate u with respect to y, partially differentiate v with respect to y, and then compare ux with vy and uy with vx. And if suppose ux is equal to vy and uy is equal to minus vx, these two conditions satisfied, then we can say Cauchy-Riemann equations are satisfied, and hence f of z is analytic function. Remember this method. Let us solve problems on type number 2. In type number 2, we have to find out analytic function f of z is equal to u plus iv. And here in this type, we have to study 4 cases. Means case number 1, if real part of f of z is given, find analytic function f of z. Case number 2 will be if imaginary part v is given, then find analytic function f of z. Case number 3 will be if u minus v is given, then find analytic function f of z. And case number 4 will be if u plus v is given, then find the analytic function f of z. So one by one we have to learn about these 4 cases. Case number 1, we are assuming if u is given. So example number 1 is find the analytic function f of z if real part of f of z u is given like this. This is algebraic polynomial x cube minus 3xy square plus 3x square minus 3y square plus 1. So solution for this, step number 1. Now here in given function, replace x by z and y by 0. Find u at x is equal to z and y is equal to 0. Replacing x by z and y by 0 here. So this is equal to x cube means z cube. Here this becomes 0 plus 3z square minus this also 0 and this plus 1. This is equal to z cube plus 3z square plus 1. Derivative of u with respect to y considering x as constant. So derivative of x cube with respect to y is 0 minus 3x into derivative of y square with respect to y is 2y plus derivative of 3x square with respect to y is 0 minus 3 into derivative of y square with respect to y is 2y plus 1 is constant, its derivative with respect to y is 0. Simplify this. This is equal to minus 6xy minus 6y. This is partial derivative of u with respect to y. Now find uy at z comma 0. Means in uy replace x by z and y by 0. Hence uy at z comma 0 is given by here minus 6x into 0, that becomes 0, and second term also becomes 0. So uy at z comma 0 is 0. Now step number 2. In step number 2, we have to consider f of z is equal to u plus iv. Then f dash z is given by ux means partial derivative of u with respect to x plus I into Vx, partial derivative of V with respect to x. Now here we have to apply Cauchy-Riemann equations. Ux is equal to Vy and Uy is equal to minus Vx. Because U is given, V is not given, so we can't find partial derivative of V with respect to x. We have to change this second term. Means replace Vx by minus Uy. So f dash z can be written as f dash z is equal to Ux minus I into Uy. Now f of z is nothing but integral of f dash z with respect to z on both sides. So f of z is equal to integral of f dash z with respect to z. This is equal to integral of partial derivative of u with respect to x, replacing x by z and y by 0, integrate it with respect to z, minus I into integral of uy, means partial derivative of u with respect to y, replacing x by z and y by 0, integral with respect to z. Okay, so without finding partial derivative of u with respect to x and without evaluation of this integral, its value direct we can write u at z comma 0 minus I into integral of uy at z comma 0, which is obtained in step number 1. Put this value in this integral as integrand 0 dz. But u at z comma 0 is obtained in step number 1, and which is z cube plus 3z square plus 1. Hence, this is equal to z cube plus 3z square plus 1 minus I into integral of 0 with respect to z, that is 0. And finally, analytic function f of z is given by z cube plus 3z square plus 1. Instead of plus 1, we can put integral constant c, and we can write here c is equal to 1, suppose. In this way, f of z is analytic function which we have obtained using these two steps. Now we have to solve problem on case number 2. In case number 2, imaginary part v is given. Then example number 3, find the analytic function f of z if v is equal to e to the power x into bracket x sin y plus y cos y. Step number 1, given that v is equal to e to the power x into bracket x sin y plus y cos y. Now, in this function, we have to replace x by z and y by 0. Hence, v at z comma 0 is equal to, we can write e to the power z into x into sin 0. Sin 0 is 0. So, this term becomes 0 plus y into y is 0. 0 into cos y. This is also 0. Hence, v at z comma 0, this is equal to 0. Now, let us find partial derivative of v with respect to y. This is equal to, considering x as constant, so e to the power x into bracket x into cos y plus, now here u into v formula. Derivative of first function with respect to y. Derivative of y with respect to y is 1. Second function cos y as it is. Then first function as it is, derivative of second function. So minus of y into sin 1. This is partial derivative of v with respect to y. Let us find partial derivative of v with respect to y, replacing x by z and y by 0. Here, replace x by z and y by 0. E to the power z into bracket z into cos 0 is 1 plus 1 into cos 0 is 1 minus 0 into something, that is equal to 0. Hence, Vy at z comma 0 is equal to z into e to the power z plus e to the power z. Now step number 2. Let f of z is equal to u plus iv. Then f dash z is given by ux plus I vx. Since v is given, u is not given. So replacing ux by partial derivative of v with respect to y. Applying Cauchy-Riemann equations, ux is equal to vy and uy. Here we have to replace ux by vy because f of z is analytic function. It must satisfy Cauchy-Riemann equation, and these are two Cauchy-Riemann equations. F dash z can be written as f dash z is equal to vy plus I Vx. But we have to find out analytic function f of z. So f of z is equal to integral of this equation on both sides with respect to z. Integral of f dash z with respect to z, which is equal to integral of vy, means partial derivative of v with respect to y at x is equal to z and y is equal to 0, integral with respect to z plus I into integral of partial derivative of v with respect to x at x is equal to z and y is equal to 0, integral with respect to z. But we know integral of partial derivative of v with respect to y at z comma 0 is given by z into e to the power z plus e to the power z. So integral of z into e to the power z plus e to the power z integral with respect to z plus I into integral of vx at z comma 0 dz. We can replace this integral by v at z comma 0 without finding integral. Direct value of this integral is nothing but value of given function v replacing x by z and y by 0. So this is equal to integral of z into e to the power z applying by parts method. First function as it is into integral of second function minus derivative of z, which is 1, and integral of e to the power z with respect to z is e to the power z plus integral of e to the power z is e to the power z plus I into this value is equal to 0. In step number 1 we have obtained value of this v at z comma 0. Hence f of z is equal to, we can write z into e to the power z minus e to the power z plus e to the power z gets cancelled plus I into 0, this becomes 0. We can add integral constant c, and this is required analytic function f of z. F of z is equal to z into e to the power z plus c. Let us solve next problem on case number 3. Remember this remark, f of z is equal to u plus iv. Then I into f of z is given by I into u plus I into I square. I square is minus 1 into v, means this is equal to minus v plus iu. Then let us assume capital F of z is equal to this f of z plus I into f of z. So this is equal to f of z is u plus iv plus I into f of z is minus v plus iu minus v. Then collecting real parts u and minus v in one bracket plus I into second bracket, taking I common from these two terms, u plus v. Let us assume real part of this u minus v is equal to capital U suppose plus I into this bracket is equal to capital V suppose. Then capital F of z is equal to capital U plus I into capital V. But from here, if we take f of z common, then small f of z taking on right hand side and 1 plus I we can take on left hand side. Then small f of z and capital F of z, relation between these two functions is given by f of z is equal to 1 upon 1 plus I capital F of z. Hence, in case number 3 and case number 4, if suppose u minus v or u plus v is given, in that case always find capital and then Small f of z you can find by using this relation. Now case number 3, if u minus v is given. Let us solve example number 4. Find analytic function f of z if u minus v is equal to e to the power y minus cos x plus sin x whole divided by hyperbolic cos y minus cos x. So its solution is step number 1. Assume capital U is equal to u minus v. Then find capital U replacing x by z and y by 0. This is equal to e to the power 0 minus cos z plus sin z divided by hyperbolic cos 0 minus cos z. But you know hyperbolic cos 0 is 1, e to the power 0 is also 1. So this can be written as this is equal to 1 minus cos z plus sin z divided by 1 minus cos z. Now we have to simplify this. Since we know 1 minus cos z is equal to twice sin square z upon 2 and sin z is equal to 2 times sin z upon 2 into cos z upon 2. So u at z comma 0 is given by 2 times sin square z upon 2 plus sin z is equal to 2 times sin z upon 2 into cos z upon 2 divided by 1 minus cos z is 2 sin square z upon 2. 2 sin square z upon 2. Now you can take 2 common from these two terms in numerator and cancels with these 2. As well as we can take sin z upon 2 common from these two terms. So this is equal to 2 times sin of z upon 2 into bracket sin z upon 2 plus cos z upon 2 and divided by 2 times sin square z upon 2. Simplify this. 2 gets cancelled, sin z upon 2 cancels with this square and remains sin of z upon 2 plus cos of z upon 2 divided by sin z upon 2. Now sin z upon 2 divided by sin z upon 2 is 1 and cos z upon 2 divided by sin z upon 2 is cot z upon 2. So this can be written as 1 plus cot z upon 2. This is u at z comma 0. Let us find partial derivative of u with respect to y. Hence, partial derivative of u with respect to y considering x as constant. In u minus v, numerator as well as denominator contains function of y. Partial derivative of u with respect to y is given by denominator square hyperbolic cos y minus cos x square of this, then denominator as it is hyperbolic cos y minus cos x into derivative of numerator with respect to y, that is e to the power y only, minus numerator as it is derivative of denominator e to the power y minus cos x plus sin x into derivative of denominator with respect to y, that is hyperbolic sin y. Okay. Now we want uy at z comma 0. This is equal to, replace x by z and y by 0 on right hand side. This becomes hyperbolic cos 0, that is 1 minus cos z. E to the power 0 is 1 minus e to the power 0 is 1 minus cos z plus sin z into hyperbolic sin 0 is 0 divided by 1 minus cos z square of this bracket. In numerator, this term becomes 0, remains only first term. Hence uy at z comma 0 is 1 minus cos z divided by 1 minus cos z square, and this is equal to 1 upon 1 minus cos z. But 1 minus cos theta is equal to 2 sin square theta upon 2. So this is equal to 1 upon 2 times sin square z upon 2. And finally, partial derivative of u with respect to y at z comma 0, this is equal to half cosec square z upon 2. Now step number 2, f of z is equal to u plus iv. This is small f of z, but we have to assume capital F of z. Capital F of z is equal to capital U plus I into capital V. Hence capital F, its derivative with respect to z is equal to ux plus I vx. But here capital U is given, V is not given. Hence applying Cauchy-Riemann equations, ux is equal to vy and uy is equal to minus vx. So we have to replace this vx by minus uy. So f dash z is equal to ux minus I uy. Hence f of z is equal to integral of f dash z with respect to z. But f dash z is this one. In ux replace x by z and y by 0. In uy also replace x by z and y by 0. So this is equal to integral of ux replacing x by z and y by 0 integral with respect to z minus I integral of uy replacing x by z and y by 0 integral with respect to z. Okay, ux at z comma 0 and uy at z comma 0. For first integral we can write this is equal to u at, for first integral we can write capital U at z comma 0 minus I into second integral uy at z comma 0 is already we have obtained in step number 1, half of cosec square z upon 2. So put here cosec square z upon 2 integral with respect to z. Hence capital F of z is equal to u at z comma 0, its value is 1 plus cot of z upon 2. Then minus I upon 2 integral of cosec square z upon 2. Integral with respect to z. Let us evaluate this integral. This is equal to 1 plus cot z upon 2 minus I divided by 2. Integral of cosec square z upon 2 is minus cot z upon 2 divided by derivative of z upon 2 with respect to z, that is 1 upon 2. Now we have to simplify this. This 2 gets cancelled with this 2, with this 2, and minus minus that becomes plus. So this is equal to 1 plus cot z upon 2 plus I into cot z upon 2. So capital F of z is, this is equal to, taking cot z upon 2 common from these two terms and 1 you can consider as constant c. So 1 plus I into cot of z upon 2 plus 1. This is capital F of z. Now small f of z means analytic function f of z is equal to 1 upon 1 plus I capital F of z. This is equal to 1 upon 1 plus I capital F of z is this one, 1 plus I into cot of z upon 2 plus 1. So simplify this. Hence analytic function f of z is equal to 1 plus I gets cancelled with this, remains cot z upon 2 plus integral constant c, assuming 1 upon 1 plus I is equal to c, and this is required analytic function. Let us solve problems on case number 4. If u plus v is given. So example number 5, find the analytic function f of z if u plus v is equal to e to the power x into bracket cos y plus sin y bracket close plus x minus y divided by x square plus y square. So let us assume u plus v is equal to capital V. Okay. Now we have to find out capital V replacing x by z and y by 0 in u plus v on right hand side. E to the power z, x is replaced by z, cos 0 plus sine 0 plus z minus 0 divided by z square plus 0. Cos 0 is 1, sine 0 is 0. So v at z comma 0 is given by e to the power z into 1 is e to the power z plus z upon z square, that is 1 upon z. This is v at z comma 0. Let us find partial derivative of v with respect to y, considering x as constant. So e to the power x as it is into bracket partial derivative of cos y with respect to y is minus sin y, and derivative of sin y with respect to y is cos y plus cos y bracket close plus derivative of this with respect to y, numerator and denominator both contains function of y. So denominator square, denominator as it is into derivative of numerator with respect to y. Derivative of x is 0, derivative of minus y is minus 1 minus numerator as it is into derivative of denominator with respect to y. Derivative of x square with respect to y is 0, derivative of y square with respect to y is 2y. Now we have to simplify this. So by we have to find out at x is equal to z and y is equal to 0. This is equal to e to the power z minus sin 0 is 0, cos 0 is 1 plus z square plus 0 square, its square here minus this minus 1, z square plus 0 square, that is 0, minus y is equal to 0 means 0 into something, that is 0. So Vy at z comma 0 is given by, this is equal to e to the power z, and this can be written as minus z square upon z raised to 4, that is minus 1 upon z square. So this is Vy at z comma 0. Now step number 2. We have to find out capital F of z. So let capital F of z is equal to capital U plus I into capital V. Hence F dash z is equal to Ux plus I into Vx. But here U plus V is given, means capital V is given, capital U is not given. So apply Cauchy-Riemann equations and replace this capital Ux by Vy. Hence by Cauchy-Riemann equations, capital F dash z is equal to Vy plus I into Vx. Now we have to find out f of z, integrating both sides of this equation with respect to z. So capital F of z is equal to integral of f dash z with respect to z, and f dash z is Vy plus Ivx. So replace x by z in Vy and integrate it with respect to z plus I. Replace x by z and y by 0 in Vx and integrate it with respect to z. But we know this is equal to Vy at z comma 0 is already we have obtained, which is e to the power z minus 1 upon z square. We can write this as z to the power minus 2 integral with respect to z plus I into, for this integral we can directly replace this integral by Vx, V at z comma 0, capital V at z comma 0. So this is equal to integral of e to the power z is e to the power z minus integral of z to the power minus 2 with respect to z is z to the power minus 2 plus 1 divided by minus 2 plus 1, means minus z to the power minus 1 divided by minus 1, minus 1. So minus minus plus 1 upon z plus I into V at z comma 0 is e to the power z plus 1 upon z. Okay. Now from these two terms we can take e to the power z plus 1 upon z, this bracket common, and this can be written as 1 plus I e to the power z plus 1 upon z. This is capital F of z. Let us find analytic function small f of z. Since we know this relation, f of z, small f of z is equal to 1 upon 1 plus I capital F of z. So f of z is equal to, divide both sides by 1 plus I, that gives f of z is equal to 1 upon 1 plus I, capital F of z is this one, 1 plus I into e to the power z plus 1 upon z. So this 1 plus I gets cancels with this, hence f of z is equal to e to the power z plus 1 upon z. If you want, you can add integral constant c plus c. So this is required analytic function and which is solution of this sum. Now we have to solve problems on type number 3. In this type, we have to solve such type of sums. Example number 6. Show that v is equal to 3x square y plus 6xy minus y cube is a harmonic function. Find its harmonic conjugate and corresponding analytic function. So here step number 1 is, first of all we have to show given function is harmonic, means this function must satisfy Laplace's equation. So v is given, v is equal to 3 times x square y plus 6xy minus y cube. Find second order partial derivative of v with respect to x and second order partial derivative of v with respect to y. Hence, partial derivative of v with respect to x considering y as constant. So 6 times xy plus 6y and derivative of y cube is 0. Again differentiate this, vxx is equal to, derivative of x is 1, 6y. Now partially differentiate v with respect to y. Vy is equal to, considering x as constant, 3x square plus 6y, 6x minus 3y square. Again partially differentiate this with respect to y. Vyy is equal to, derivative of this becomes 0, derivative of this also becomes 0, and derivative of minus 3y square, it is minus 6y. Now from this and this, it is clear that vxx plus vyy is equal to 6y minus 6y is equal to 0. Means Laplace's equation is satisfied. Hence, this implies v is harmonic function. Now, step number 2. In step number 2, find v at z comma 0, replacing x by z and y by 0. That gives 0 plus 0 plus 0. 0 plus 0 minus 0 means v at z comma 0 is 0. Let us find vy, partial derivative of v, which is already obtained in step number 1 and which is equal to 3x square plus 6x minus 3y square. Now we have to find out partial derivative of v with respect to y at x is equal to z and y is equal to 0. Vy replacing x by z and y by 0. This is equal to 3z square plus 6z and this becomes 0. Now in step number 3, f of z is equal to u plus iv. F dash z is equal to ux plus I vx. V is given, u is not given. So applying Cauchy-Riemann equations, ux is equal to vy and uy is equal to minus vx. We have to replace ux by vy. So f dash z is equal to vy plus I into vx. This is f dash z, but we have to find out f of z. So integrate both sides of this with respect to z. F of z is equal to integral of f dash z with respect to z. This is equal to integral of vy replacing x by z and y by 0, integral with respect to z plus I into integral of vx replacing x by z and y by 0, integral with respect to z. This is equal to this value vy at z comma 0. This is vy at z comma 0 is 3z square plus 6z. We can put here integral of 3z square plus 6z integral with respect to z plus I. Value of this integral is given by v at z comma 0, and v at z comma 0 is 0. So this is integral of this 3 into integral of z square with respect to z is z cube divided by 3 plus 6 into integral of z with respect to z is z square divided by 2 plus I into 0. So after simplification, f of z is equal to z cube plus 3 times z square. This is analytic function f of z. Now step number 4. We have to express f of z in the form of u plus iv, replacing z by x plus iy. So put z is equal to x plus iy in equation number 1. Hence f of z is equal to x plus iy cube plus 3 times x plus iy square of this. Expand this and separate real part and imaginary parts. This is equal to x cube plus 3 times x square into iy plus 3 times x into I square y square plus I cube into y cube plus 3 times expansion of this bracket x square plus I into 2xy plus I square y square minus y square. Simplify this. So this is equal to x cube plus I into 3 times x square y. I square means minus 1 minus 3 into x y square. I cube means minus I y cube plus 3x square plus I into 3 into 2 6xy minus 3y square. Now correct real parts. Real part is x cube minus 3xy square plus 3x square plus 6xy minus 3y square. Here I into 6xy. So collecting real parts first. X cube minus 3xy square minus 3y square plus 3x square, this one and this one, plus I into imaginary part, this term 3x square y, this term minus y cube, and this term plus 6xy. This is u and this is v. So this is equal to u plus iv, where u is equal to x cube minus 3xy square minus 3y square plus 3x square. This is harmonic conjugate of given function v. Now type number 4, orthogonal trajectory. Example number 7, find the orthogonal trajectory of the family of curves x cube y minus xy cube is equal to c. So this is given function. Solution for this, let given function is suppose u is equal to x cube y minus xy cube is equal to c. Now as usual method, step number 1, in step number 1 find u at x is equal to z and y is equal to 0. So this is equal to, this becomes 0 and this also becomes 0. U at x comma z and y comma 0 is y is equal to 0 is 0. Now find partial derivative of u with respect to y considering x as constant. So x cube derivative of y with respect to y is 1 minus y cube, its derivative with respect to y is 3y square minus 3 times xy square. Okay. Now what we have to do? Find uy at x is equal to z and y is equal to 0, which is equal to z cube. This term becomes 0 if we substitute y is equal to 0. Step number 1 is over. Now step number 2. In step number 2, let f of z is equal to u plus iv. Then f dash z is equal to ux plus I into vx. But we are considering u is equal to given function, means v is not given. So applying Cauchy-Riemann equations, ux is equal to vy and uy is equal to minus vx. So replace this vx by minus uy. F dash z is equal to ux minus I into uy. Okay. Then step number 2, here we have to find out f of z. F of z is nothing but integral of f dash z with respect to z. But f dash z is this one, so its integral, this is equal to integral of ux at z comma 0 dz minus I into uy at z comma 0 dz. But this integral, its value direct we can write u at z comma 0 minus I into value of this integral uy at z comma 0, this value is z cube dz. Okay, now u at z comma 0, in step number 1, we have obtained value of u at x is equal to z and y is equal to 0, which is 0 minus I z cube, its integral with respect to z is z to the power 4 upon 4. This is f of z. F of z is minus I into z to the power 4 upon 4. Hence f of z is equal to minus I upon 4 z to the power 4. Z to the power 4. In step number 3, put z is equal to x plus iy and express f of z in the form of u plus ib. So f of z is equal to minus I upon 4 x plus iy to the power 4. Applying binomial expansion formula, we can expand this up to the power n is equal to 4. Binomial coefficients will be 1, 4, 6, 4, 1. So this is equal to minus I upon 4 into bracket x to the power 4 plus 4 times I into x cube y plus 6 times I square into x square y square plus 4 into I cube x into y cube plus 1 into iy to the power 4, I to the power 4 into x to the power 4. Simplify this. So this is equal to minus I upon 4 x to the power 4 plus I into 4 times x cube y, I square means minus 1, minus 6 times x square y square, I cube means minus I, 4 times x y cube, I to the power 4 is 1 plus x to the power 4. Now multiply this bracket by minus I upon 4. So this is equal to minus I into I, 1, 4 upon 4 x cube y, x cube y minus xy cube, this is real part, plus I into 6x square y square minus x raised to 4 minus y to the power 4 divided by 4. This is imaginary part. This part is already given in question in the statement of problem, and this is value of imaginary part v. So v is equal to, we can write 1 upon 4 times into bracket 6 times x square y square minus x to the power 4 minus y to the power 4 bracket close. This is equal to c. So this is a required answer, means orthogonal trajectories of the family of curves of u is equal to c1 is nothing but this v is equal to c. This is final answer. Let us solve problems on type number 5. Name of this type is harmonic identity. Before that, we must know z into z bar is equal to modulus of z its square is equal to modulus of z bar square of this. Similar to this, replacing z by f of z and z bar by f of z bar. F of z into f of z bar is equal to modulus of f of z its square is equal to modulus of f of z bar square of this, and f dash z into f dash z bar is equal to modulus of f dash z square of this is equal to modulus of f dash of z bar its square, and this is harmonic identity. Dou 2 by dou x square plus 4 times dou 2 by dou y square is equal to 4 times dou 2 by dou z into dou z bar. Now let us solve example. Example number 8. If f of z is analytic function, then prove that into bracket dou 2 by dou x square plus dou 2 by dou y square. This operator we are applying on square of modulus of f of z, and which we have to prove 4 times square of modulus of f dash z. So Let us take its left hand side. Solution for this, LHS is equal to dou 2 by dou x square plus dou 2 by dou y square bracket close, which we are applying on modulus of f of z its square. But we know modulus of f of z its square is given by f of z into f of z bar, and this harmonic identity we can replace by 4 times dou 2 by dou z into dou z bar. So we can write LHS is equal to 4 times dou 2 by dou z into dou z bar into modulus of f of z its square can be written as f of z into f of z bar. Now separately apply dou by dou z on f of z and dou by dou z bar on f of z bar. So this is equal to, we can write 4 times dou by dou z into dou by dou z bar, which is nothing but dou 2 by dou z into dou z bar. We are applying this on f of z into f of z bar. Dou by dou z apply on this and dou by dou z bar apply on this. So this is equal to 4 times dou by dou z f of z into dou by dou z bar f of z bar. But dou by dou z f of z is nothing but f dash z, and dou by dou z bar f of z bar is nothing but f dash of z bar. So this is equal to 4 times f dash z into f dash of z bar. But we know f dash z into f dash of z bar is modulus of f dash z its square. So we can write this is equal to 4 times modulus of f dash z square of this, and which is right hand side of the statement which we are proving. So in this way we can solve problems on type number 5. Let us stop here. Thank you. Thank you all. Thank you for watching this video. Thanks.